so it's a giveaway for most observers. But the point is that, not just a picture, of course, then you go more quantitative, and you can actually prove that simulations like this are able to capture the large-scale diversity of the galaxy population. So we're not doing surveys, we're not doing observations, we're making fake universes. I like to call them universes in a box. The simulations are literally a box. That's why I'm showing you the cube. This is a simulation in a periodic cube. I'm showing you the dark matter density, so the large-scale cosmic web of dark matter. You see sheets, filaments, nodes, right, where halos are, and you see voids. And so the goal with these kinds of simulations, right, is to understand the physics of galaxy formation, to develop a theory for galaxy formation and galaxy evolution. And we want to do that across the entire mass spectrum that galaxies exist, all the way from little dwarfs up to massive clusters, and we want to do it across all of cosmic time, essentially over which galaxies are observed to exist, all the way from ionization down to the present day. And the tool of choice are called cosmological hydrodynamical simulations. Cosmological means that the initial conditions start from lambda CDM, they start from the statistics of the CMB. Cosmological also means that these are large representative volumes of the universe, not single galaxies, for example. Hydrodynamical means not just dark matter and gravity, like the Millennium simulation I showed earlier, but also the baryonic physics of the gas, the stars, the supermassive black holes, and all the messy astrophysics which comes along with that. In this picture, a galaxy is very small, below the size of a pixel on this projector. If we zoom in all the way to a single pixel, this is what we see. So these are images of simulated galaxies. These are stellar light mocks. So these are in the James Webb bands, if you like. They're pretty examples. You see all kinds of different things. You see a thin edge on disks. You see warps. You see giant bars. You see mergers, interactions. You see boring, spheroids, ellipticals. These are all galaxies which have co-evolved and formed within one of these large simulations, in particular, this simulation called TG50. So TG50 is one of the 3 simulations of the illustrious TUG project. I just flashed this image. I think a lot of us have seen this many times. This project is simply not 3 simulations of large-scale galaxy formation. It kind of represents the modern state of the field for these cosmological hydrodynamic simulations. Each of them is solving for the coevolution of these 5 components. You want to know what is in a simulation like this? It's dark matter, gas, stars, black holes, supermassive black holes, and magnetic fields in the case. This is not the only game in town. You've probably heard of lots of these names. Eagle, Horizon AGN, Simba, right? There's simulations for larger volumes or simulations of higher resolution, but they're all similar in what they're trying to achieve. And they're all trying to solve the same problem, which is the problem of galaxy formation. In galaxy formation, it's a very physics-rich problem, but it's also very multi-scale, which is why it's so hard. By multi-scale, what I mean is that there's an enormous dynamic range, both in space and thus in time. And I like to emphasize that with this picture, right? So we're starting off at gigaparsec scales, where you actually realize the isotropy and homogeneity of the universe, right? Everything is the same. We zoom in, down to the scale of an individual collapsed structure. That's a dark matter halo. Down, zoom in by a factor of 1,000. Zoom in again another factor of 100 or so, you get to an actual galaxy, right? The size of a spiral disk galaxy, say. But you have to zoom in again by a factor of 1,000,000 or so to get to the actual sites of star formation, or in this case, accretion disks around a supermassive black hole. And what's fun to point out, of course, is that it's not, information is just not flowing in one direction. It's just not headed downwards, right? This is not just collapse. Because there's a back propagation of information from the smallest scales back to the large scales. And a jet from a black hole is a perfect example. So a jet launched on these scales, we know, can influence the halo, the entire halo on these scales, a factor of 1 billion larger. So it's very challenging from a computational perspective. This is my slide for the aficionados. I don't want to go through it at all. To solve that problem, we turn to a code. In our case, this code is called REPO. REPO is fundamentally a fluid dynamics code plus gravity, right? Its defining feature is that it's solving a gas dynamics equation on an unstructured Voronoi moving tessellation of the spatial domain. which is a very fancy way of saying that it solves the gas equations well. This is our numerical foundation. On top of that, we start to build the astrophysical model that we need to simulate galaxies. So we start with microphysics of gas, cooling and heating, the formation of stars, stellar evolution, stellar enrichment, most importantly, stellar death, supernova, explosions, and outflows driven by supernova, and then of course supermassive black holes, how they form, how they merge, how they accrete gas, and again, most importantly, how they do their feedback, right? How they release energy back into the surrounding medium. This whole slide collectively is what we mean by the galaxy formation model, which these illustrious TNG simulations have been run with. It's a combination of the numerical framework plus the astrophysics on top. What does this complicated slide gives us? It gives us a nice, pretty movie to look at. So this is a movie of an assembly of a galaxy, right? From early times, redshift counter in the upper right, down to the present day. This is going to be between Milky Way and Andromeda by redshift 0. And the main panel is gas density projection on the scale of the halo. So this would be like the virial radius of the halo. This is an inset showing you the stars which are forming just in the very center. That's the galaxy itself. It's in the middle of this image. It's not a galaxy. We're redshift 2.6. It looks to me like a blob of turbulent gas, which we think is how galaxies of this mass actually look at these redshifts. As time goes on, we're past redshift 2, things actually settle down. Notice there's kind of a phase transition which happened. Actually, the gas settled into a rotationally supported thin pancake, always known as a disk galaxy. It's almost edge on, right? There's a merger, comes in. You see this, come back and tweak around the stellar disk. If you look in the lower right, actually that minor merger forms a gigantic bar. You see it starts to spin around. It's a very quiescent galaxy. So from now to redshift 0, it's basically going to be evolving, slowly spinning. But what is he doing? He's driving the baryon cycle. If you look carefully, there's lots of stuff going out. There's lots of stuff coming back in. We call this the galactic fountain, this cycling of material in and out of a star-forming galaxy. And this baryon cycle is what's regulating the stellar growth and actually the evolution of this galaxy. It's the flows of gas, not in the galaxy itself, but in the halo, in the atmosphere of this galaxy. If you looked very carefully at that movie, you probably noticed that when stuff was flowing out and flowing in, it wasn't happening in all directions equally. In fact, outflows and inflows around the galaxy tend to happen in very preferential directions. So I'm showing you one example of a galaxy here, low mass, similar to the one we were just watching. It's edge on. Right, I place the disk edge on in the center. On the left, you see gas metallicity, solar metallicity, yellow, 10th solar, and green. On the right is radial velocity. So red is outflow. That's just the convention. Negative green is inflow. What do you see? Along the minor axis direction of a disk galaxy, you preferentially find rapidly outflowing gas, which is substantially enriched. And so this is a galactic scale outflow, which is pulling out metal-enriched gas from the disk and polluting the entire atmosphere of this galaxy with this medium velocity, medium temperature, pretty enriched gas. Clearly, the star formation activity in this galaxy is having a pretty profound impact on its halo. And imagine you trace your finger around this circle, right, along an angle with respect to the disk. You can probably imagine that physical properties of the halo gas are quite different in different directions, right? In particular, the metallicity. So if you look at the metallicity along the major axis direction, it's the lowest. This is metallicity as a function of this angle. If you look at the metallicity on the minor axis, of course, it's the highest. This is an enrichment signal from outflows as opposed to a dilution signal from cosmic gas accretion coming from inside. So not only could observationally we see such a signature of the metallicity of the halo as a function of angle, but this is really encoding the physics of feedback, of supernova feedback in this case, that's going on in the central galaxy. There's another quite epic feature we heard a lot about last week, which is very directional in nature. These are the galactic center bubbles, right? As seen in gamma rays in red and in X-rays in cyan in our own Milky Way galaxy. So these are all sky data image. Sagittarius star, our supermassive black hole, right in the middle. These are fast, hundreds of kilometers to 1,000 kilometers a second. Outflows, super virial, fancy way of saying they're hot. Temperature is hotter than the virial temperature of the hot halo surrounding them. These are striking features, I would say, which have been recognized, pointed out more and more. We heard about this last week from Gabriele Ponti. In these simulations, we see very similar features emerging from Milky Way-like galaxies. So the bottom left-hand corner is the real X-ray emission map of the sky. These are the E Rosita bubbles and X-ray emission. The gallery is a gallery of simulated disk galaxies. They're all been placed edge on, just like before, again in X-ray emission. And what we find is that galactic center bubbles like this are common, actually. So these are actually a bit larger scale. Probably this one is the closest in scale to the true Fermi bubbles, the Rosita bubbles, right? Quite small. A lot of these are bigger, clearly corresponding to older epochs, past outflow events. So if the simulations are telling us anything at all realistic here, there's a few immediate points. The first one, so I often forget to say it, but it's the most important. In the simulations, these bubbles are produced by the black hole. We can prove that without a doubt. In fact, it's black hole energy injection in the low luminosity state. So the black hole is not accreting very much, just a little bit. And in this state, it drives a very efficient, very fast kinetic wind. This is the physics behind the galactic center bubbles in these TNG simulations. Second, we expect, as you can see from the pictures, that in our own Milky Way galaxy, right, the Fermi bubbles and Rosita bubbles should be mimicked, or there should be replicas of them, which are larger and more distant and fainter, which would correspond to previous episodes of feedback energy. And third, we actually expect such features to be common, I mean half or more of all galaxies of this mass scale in external galaxies. So if we went and looked, we should find them everywhere. Okay, but that's hard. Why is it hard? This is very diffuse gas. This X-ray emission is very dim. It's very hard observationally to find them. How could we find such features? We could do something like LEM. LEM is a X-ray emission concept for the future. It's an IFU for X-rays in space. It's kind of like PRISM, which will launch next year. If you're familiar with this, this is the replacement of Atomi, kind of like Athena, except it has a much larger field of view, has extremely high spectral resolution, which lets you map out the actual motion of gas, only for soft X-rays. It's perfect for looking at the circumgalactic media of Milky Way, normal kind of galaxies. This is a concept proposal to be submitted next year. The idea is, let's look at 100 or so nearby Milky Way-like galaxies. Let's stare at each for a megasecond, for a million seconds, and actually make a map of the hot circumgalactic medium around galaxies. I think a lot of the reason people are so excited by a concept like this is because the hot circumgalactic medium has a lot of information and it's very hard to see it. It's very hard to access that information. We'll come back to another picture of an outflow being driven from a galaxy. I'm moving up in the mass scale. I'm going to even more massive galaxies, 5 times as big as the Milky Way, actually 2 as well. This is a big outflow being driven by a supermassive black hole at the center from a disk. Again, I put it edge on. The little white dot down there is the kind of sphere of influence. It's where the energy is actually injected from the black hole, and it creates this gigantic bubble. These are way larger features than what I was showing you before on the scale bar. Hundreds of kiloparsecs large, halo scale outflows. They look like cocoons, right? Kind of a pile-up feature. You have density enhancements on the edges, really enriched gas being pulled out of the center, out of the galaxy, super high velocity, thousands of kilometers a second, and very, very hot as this energy shocks and gets converted into heat. These outflows actually clearly really mess up the halo. Right? They have a profound impact on the atmosphere of this galaxy, and they're starting to get really strong wind. That gets really strong when the galaxy starts to quench, actually, right? So galaxy starting to quench means a really strong feedback from a supermassive black hole is pulling the galaxy off the star forming main sequence, inhibiting its star formation rate and simultaneously perturbing the circumgalactic medium by driving this large scale outflow. So take a bit of a thought experiment here. At the transition mass regime of galaxies, that means halos of 10 to the 12, that means galaxies like the Milky Way. This is where you have a mix in the galaxy population of blue galaxies and red galaxies at the same mass scale. What turned you from a blue star-forming galaxy to a red galaxy is a quenching process. And in these simulations, when we go and look at the gas that surrounds these kinds of galaxies, around blue galaxies, blue star-forming galaxies, this is what we see. These are pictures of gas on the scale of the halos. The circles are, again, the virial radii of halos. Galaxies are very small in the center. I'm showing you something in particular called oxygen 6, 5 times quintuply ionized ions of oxygen. So an oxygen atom which has lost 5 electrons seems a bit random. This is observable and often observed. And so this is an observational tracer of the warm, hot gas around these halos. And what you see is that blue star-forming galaxies, they have a lot of it. Right? Their halos are filled with this kind of warm oxygen 6 rich gas. But red galaxies, at exactly the same mass, don't. You can just see by eye. They're exactly the same mass galaxies, but they're severely deficient in the amount of oxygen they should have had if they had still been star-forming. And why? Because their black hole has started to quench those galaxies, has started to generate these really big outflows, heat up the circumgalactic medium, and remove the oxygen 6 from these halos. So we actually interpret this kind of dichotomy as a direct impact of supermassive black hole feedback, or AGN-driven outflows, on the halo gas of these systems. In particular because the black holes heat up the oxygen, push it out of this particular ionization state, and they also rarefy the gas. They lower the density. They actually physically kick away the oxygen. This kind of dichotomy between red and blue is also very clear in the X-ray emission from halos. I want to show that to you here. So star-forming galaxies have more X-ray light than quenched galaxies. An exact analogy to what I just showed you. So this is X-ray luminosity. It's a function of K-band magnitude. I prefer stellar mass on the top. All this is from the simulation. So the blue contours, empty and filled, star-forming galaxies from the simulations. The red contours, quenched galaxies from the simulations. And if you look at the overlap region, right, where you have both blue and red galaxies, this is the Milky Way mass regime, this is the transition mass regime, what you see is that star-forming galaxies have preferentially higher X-ray emission than their quenched counterparts. So X-ray emission goes like density squared, temperature to the 1/2, some weird function of metallicity. And it's actually the density which wins. So it's because the black hole feedback pushes out so much gas out of these halos, lowering the density, that the X-ray luminosities get pulled down. So this is preventative feedback, if you've ever heard this term before. You have two kinds of feedback. You have ejective feedback, which you throw it away. Or you have preventative feedback, it means you stop it from coming in the first place. By lowering the density of the halo gas, you make the cooling of that gas much less efficient. So in the future, the hot circumgalactic medium will not be able to cool onto the galaxy, will not be able to sustain star formation in the future. I can throw in some data. Surveys like Atlas 3D or massive, probe the X-rays of red quenched galaxies, and there's a little bit of data on the other kinds of late type or star-forming galaxies. Perhaps if you squint, you can see a bit of a hint that in existing data, this kind of dichotomy is suggested. But actually, our main target here is E Rosita. Right? So it's statistical. What if you stacked millions of blue galaxies and millions of red galaxies and looked at how the X-rays from their halos differ? In fact, people have done that and now started a lively debate whether or not this has actually been seen already in the initial data from E Rosita. The reason this regime, transition regime of galaxies is so interesting because galaxies are so diverse, right? So we looked at this, we take a sample of Milky Way-like galaxies from the simulation. There's about 130 of them in this TB50 simulation. What I'm showing you here is just the fraction in each of cold gas. So how much of the mass of that halo is cold gas? And as you look at the number, just look at the bumpiness. Right? Some galaxies have a little, some galaxies have a lot. These are all in a very narrow mass range between 10.5 and 10.9 stellar mass, roughly speaking. They're all Milky Way-like. There's a huge diversity in their circumgalactic medium properties. Let me add on a few more lines. Pick a favorite color. Red is warm gas, blue is hot gas, orange is the stellar mass of the galaxy, gray is the total mass, green the metal mass. Pick a color, try to see if you see any trend as you go from the left to the right. You really don't, right? Which is to say, the properties of the halo, the properties of the CGM gas don't depend on the stellar mass of the galaxy. This is ordered in stellar mass, roughly speaking. Clearly, they depend on something else, right? They know about the feedback, they know about the outflows. This is what we've been saying. So let me give you a plot. The total amount of gas mass in the CGM and the halos of galaxies is a function of stellar mass. This is the same sample we were just looking at. All the colored dots, there's one galaxy for each colored marker. Do you see any trend with the stellar mass? No, it's kind of flat. If I show you instead of the total CGM gas mass, the amount of cold gas in the halo, it's also kind of roughly flat. There's no strong dependence on stellar mass. Okay, but what do you see in the color? Look at the color. The color is the specific star formation rate of the galaxy. So if the galaxies are quenched down here, they have significantly lower amounts of gas in their halos. If they're still star forming, they're on the main sequence, they're blue, actually are enhanced. They have more gas still in the halos. So why is this? It's like a chicken and egg problem. You could have had, say, less cold gas in the halo over here. So then this was less cold gas to fuel star formation. This is why your star formation rate is lower. Or perhaps the reason your star formation rate is lower is because your black hole has started a really energetic feedback activity, which has suppressed your star formation rate and also kicked gas out of the halo. In fact, it's the latter picture, right, which is our overall interpretation. So clearly, these systems which have much lower amounts of gas in the halo, the gas must have gone somewhere. In fact, it must have left the halo. This is the total amount of gas within the virial radius of a dark matter halo. So if it's not there, ready to go, it went farther away. So put on your dark matter goggles, I like when people say this. Imagine you can take a picture of dark matter and zoom out. And zoom out a lot. So this is a halo. That's the virial radius, the little white circle, in dark matter density. That's what an NFW halo looks like. This is the same halo in gas. This is the gas distribution on the same scale. Okay, it's two pictures of the big halo. But if we take the ratio, so if I show you the fraction of gas relative to dark matter, this is the baryon fraction. This is a picture. This is what you get. So what are we seeing here? This is baryon fraction relative to the cosmic mean, relative to how much you should have had. If you have the cosmic baryon fraction, the color's white. If you're missing your baryons, if they've gone somewhere else, you're blue. And if you have too many baryons with respect to the dark matter underneath, you're red. So what do we see? In the very center of this halo, that's the galaxy. That red structure is a baryonically dominated galaxy. It has lots of gas, but even more, there's lots of stars. There's lots of baryons. Baryons dominate over dark matter inside the galaxy. But the halo itself is this blue ball, right? So the halo itself is missing all of its baryons. It's been severely depleted of the gas, mostly, that it should have had. And where did it go? You can actually see a kind of like a ring of red, right? If you squint. So actually this mass has piled up outside of halos. What's the first thing you would do with a picture like that? I would make a profile, a radial profile. The simplest statistic you can come up with. So I'm going to show you the same quantity was in the image, a baryon fraction, normalized to the cosmic mean, as a function of distance away from galaxies. So if we have a proper amount relative to the amount of dark matter, we should be here at the cosmic value. And I'm going to show you a line for galaxy clusters. The most massive halos in the universe, 10 to 15 solar mass galaxy clusters. What do we see? Well, it's basically flat. It's basically 1. This is why people say that clusters are closed boxes. Right? They're black holes, their feedback. It's not enough energy there to win versus gravity. So in fact, you only need to go out to about half the virial radius. This line is 1 times the virial radius to recover all the baryons which should have been in that halo. But we go down to lower masses, these are groups, 10 to 13, 10 to 14 halos. You see that actually inside the halo, they're severely deficient. They're missing all of their baryons, and they've piled up at actually quite large distances, 2, 3, 4 times the virial radius. These are megaparsec scales away, that this gas has been pushed due to black hole feedback. Let me keep going down the mass scale. This is 10 to the 12 and 10 to the 13. These are kind of Milky Ways at this point. So where the effect is actually most strong, right? Down even further, so now we're below Milky Way mass scales, LMCs. Again, you see that inside the halo, you can see most of the gas is piling up outside. You go down even further, even further. What am I even showing you down here? This is clusters. These are so small that there are no galaxies in these halos. So this is the regime we call dark subhalos. The gravitational potentials of these halos are so weak that they can't hold on to any gas whatsoever. So no stars form, and no luminous galaxies exist at all. So by combining all of these simulations together, we're actually able to show you how the gas is distributed over the full range of halos where galaxies even exist, from the smallest to the largest. I want to collapse this picture, put it in 2D, right? There's a lot of trends with mass, it's kind of confusing. I like this view a bit better. This is halo mass. Again, from the smallest things to the most massive things as a function of distance. And the color is showing you the baryon fraction again. So where it's black, what does it mean? Black means you've reached the cosmic value. You found all of the associated baryons, there's no baryons missing. Where it's bright, all the gas is missing. Right? The baryon fraction is very low. At the top, we have this regime of clusters. So you only need to go out a little bit to get black, to find all the associated baryons of those halos. Then we have a regime of groups and Milky Way mass systems where supermassive black hole or AGN feedback really dominates, right? It's so powerful that it can eject mass out to hugely distant scales away from these halos. This funny break here, and this is because the feedback mechanism which dominates is shifting from the black holes to the stars. This is the regime of low mass galaxies where winds driven by supernova, type 2 mostly, are doing the work, but actually very similarly to the black holes, right? Driving gas out to very large scales. And then at the very bottom, we have this regime I call ultraviolet background heating, which again just means heating from extragalactic radiation is strong enough to prevent gas from ever cooling and ever accumulating in those halos. So there's no galaxies at the very bottom. And if you look by eye, try to find like a demarcating line between the black region and the colored region, and you pick out something which looks like that. So what is that line? It's quite important. It tells you the radius you need to go out to find all the missing baryons, if you like that phrase, or to find all the baryons which have been distributed by astrophysical feedback processes. So this we call it the closure radius. The definition is pretty simple. The distance out to which all the baryons associated to that dark matter halo are found. This is the answer. This is the closure radius as a function of halo mass, same scale as before. This line is for the TNG simulation. So 0.1, it's huge. This is 10, this is 20. So for low mass galaxies, for stellar feedback, stellar winds throwing stuff out, actually you have to go out to 10 times the virial radius to find all the gas, which should have been in the galaxy. Come down, 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 until there's some minimum. What is this? This is the onset of strong supermassive black hole feedback. It occurs at the Milky Way mass scale, roughly. Supernova feedback is becoming weaker and weaker, right? The halos are growing and growing, potentials are getting stronger and stronger. Eventually, it can no longer regulate star formation. The black hole takes over, starts to drive very powerful winds, and that ejects material again out to large distances. It's this pretty funky curve shape. Then again, halos are getting bigger, potentials are getting stronger. Black hole feedback can no longer do much to compete against gravity until you reach the clusters, right? Where the closure radius is the virial radius. We call these closed systems. As for TNG, other simulations are quite different. And so green is another cosmological simulation called Simba. Purple is another cosmological simulation called Eagle. They're very similar in what they're trying to do and how they're doing it, but the astrophysical models are different in each, right? How they treat black holes, black hole feedback, how they treat supernova, they're quite different. So SIPA looks a bit green like changing, but much stronger, right? We have to go even farther out to find the baryons. So clearly, this feedback model is much more objective. The purple line, Eagle's simulation, is quite different. There's no bump. There's no non-monotonicity. There's no onset of strong AGN effects. Right? Clearly, the model for black hole feedback is much more smooth as a galaxy grows. So why is this interesting? Because we can find this. We can find this observation. We can find this in X-rays, where the Sunyaev-Zeldovich effect at very large distances. So by mapping out the distribution of baryons of gas on extremely large scales, we can actually constrain the different feedback models that we're currently using in these kinds of cosmological simulations. I wanted to close, going back to the data, talking about how we can observe other phases. I'm not going to do it. I just want to skip through it really quickly. I want to talk in particular about looking at the CGM gas in emission. This is kind of the forefront, in my opinion. We all have in mind the idea of absorption, how we can probe gas and absorption, but now, thanks to new integral field unit spectrographs, MUSE and KCWI in particular, we can actually take pictures of this CGM gas in emission. This is very fun, and to connect from the point of view of simulations, we need to do forward modeling. We need to, for instance, account for the resonant scattering of Lyman alpha photons as they go through space. I'm going to jump through this. We can then take a picture of simulated CGM as it would be observed by one of these instruments. We can compare surface brightness, radio profiles. We can start to ask, is the distribution of cold gas in these halos realistic? I've talked a lot about the hot gas and X-rays. Lyman alpha traces cold gas, completely different phase. And we can start to understand the origin and where this gas comes from. In the end, we want to ask the question, could we actually take a picture of the cosmic web? So the cosmic web itself, a large-scale structure, could we see it in the light of Lyman alpha? This is kind of where we're going in the future. I'll leave it as a cliffhanger for the future. So let me end here with a favorite picture and one takeaway message, which is that understanding the gaseous halos of galaxies, the atmospheres of galaxies, is the key to understanding galaxy evolution. Why is that? The reason is because astrophysical feedback processes deep inside the galaxy itself, fundamentally reshape those gaseous halos. Thanks.
Thank you very much, Dylan. As an observer, I guess it's really extremely exciting also to see this connection that we're making between new observatories able to look at these lines and these simulations. I'm sure there's lots of questions. This fascinating picture that you had of galaxies similar to the Milky Way, where you had a set of blue galaxies selected from the simulations of red, and you showed that you are thinking in terms of feedback from the AGN as controlling the precipitation of cold gas, stopping the cold gas forming and also burning it out. The question is, what is the statistical properties of the black holes at the center of these galaxies on the blue galaxies compared to the red galaxies?
It's a great point. So it's actually what we think is one of the key observable signatures of this dichotomy of the oxygen 6 between the blue and the red galaxies. There's also this dichotomy of the X-ray between the blue and red galaxies. And the answer is that the red galaxies must have more massive black holes. Why? Because total energy released by a black hole is a monotonically increased fraction of the black hole mass. So by definition, these have somewhat larger black holes than these. And if that was not true observationally, that would rule out this picture.
But I mean, presumably you can measure the mass of black holes in all the galaxies you have, right? So
I'm saying from the simulation point of view,
yes,
that's the expectation. But this has not been verified observation.
Okay, okay, so you see that. Can I also ask, as I see not yet any more questions, why is it in the evolution of the galaxies that this set of galaxies has a large higher black hole mass than the other set, even though they have a similar halo mass? Is that due to the differences in the merger history of both the black hole halos and the galaxies themselves? Is that the main reason?
Presumably, I mean, that's the origin of these kinds of dichotomies, right? If the reason you can have a mix of star-forming crescent galaxies at the same mass is that they must have had different assembly histories, different evolutionary pathways. That could be faster early growth, or faster late growth, or different precise mergers. The details, of course, are complex. I don't have a single answer for you there, but you're right that the reason a galaxy is red versus blue at a given mass is because it must have had a different assembly history.
Okay, thanks. And I guess you verify that because you actually see everything that happens with all the galaxies, right? I mean, you can verify that.
This is our excuse of using the simulations as a time machine. We can always rewind and look at why something came to be in a way which is somewhat easier.
Okay, thank you very much. That's fascinating. I just pass on to Ralph Kudritz.
Very interesting stuff there. The question is, the AGN-driven outflows, are these primarily magnetohydrodynamic winds driven from the black hole or the surrounding disk, or is it more a photo X-ray driven flow process from the X-ray fields themselves?
Yeah, so keep in mind that these kinds of simulations, the feedback coming from the black hole is by definition a sub-resolution model, or what you call subgrid model. In particular, in these simulations, the mode of feedback which is doing everything interesting is this last one here, which we call a high velocity but non-relativistic wind, which is launched from the accretion disk, in particular, from a radiatively inefficient accretion disk. This is following something called the adios convection-dominated solution model. So it's not a jet, it's not relativistic. But again, this is kind of the motivational physics for what is ultimately a very simple sub-resolution model, right? And the simulation is actually running. We just have to decide how much energy, in what form, and where does it go.
Okay. And to follow on with that, is the difference between Eagle and illustrious simulations in that regard due to the way you're handling the outflows from the AGN?
I think so, yes. So in this last, when I was contrasting the difference of behavior and the fact that in 2 out of 3 of the simulations, you see quite a change of behavior due to the onset of strong AGN activity, but you don't see it in the purple line. It's exactly because in the purple model, the Eagle model, there's not a switch of behavior put in. So in the TNG and the simple models, there's an assumption built into the model that after the black hole becomes massive enough, or more accurately, when the accretion rates on the black hole drops low enough, there's a fundamental switch of the mode. So the physics changes, and the energy injection physics is different. So we switch, this causes some change of behavior. In Eagle, that's not there. So in Eagle, it's a simpler thermal energy injection, which happens irregardless of the accretion rate. So there's never a change of a step function change of behavior, if that makes sense. So those are 2 very different underlying assumptions of these 2 different classes of assumptions about the activity of the black hole as a function of its accretion rate, radiatively efficient versus inefficient states.
So this is super cool. But my question is, I think, in the same spirit of life. I'm wondering what are the uncertainties in the underlying model. I mean, you show one example where the differences in the physical documentation lead to notice the difference in this particular quantity, right? There are many quantities which work very well because otherwise they would not be in. The models are adjusted and gauged and validated in many galaxy properties. Now, I'm wondering what would need to be done to also keep these things done. In particular, I'm asking about what needs to be done to get predictions of nuclear, because you see galaxies, you see many galaxies, and if the uncertainty in the, let's say, implementation of the baryonic physics is larger than the statistical uncertainty, that you would need to pin down different, cosmological models and so on. How can we approach that problem?
There's many questions in your question. Let me address one. So in all of these models, there are many free parameters. There are many aspects which have been specifically calibrated to match certain types of data. For instance, the stellar mass function of galaxies, which is 0. This is our most important observable. All of these models use that as a calibration, as an input. But this is the large-scale distribution of baryons. This is an output. This is entirely predicted. This is not observed in any way yet. So by observing it, we can make a selection on these models and a posteriori. Hope that somewhat answers your question.
So if you could quantify the uncertainties related to the different value subgroup models, would you say we talk about 10% uncertainty?
Are you saying how much do I believe that any one of those curves is actually correct? Wow, that's, yeah, I wouldn't phrase it like that. I mean, I certainly don't believe any of these curves, but they're all, each of them is a singular theoretical prediction for a future observation. Undoubtedly, if a future observation has nice points with little error bars, of course, all of these will rule them out for sure. The question is maybe one will be closer to the other. Good feature is this bump, right? Is this bump actually indicative of a change of the physics of black hole feedback or not? If we could actually constrain this monotonicity or not, I think that would tell these kinds of simulations quite a lot about the underlying black hole physics. Yeah. But quantitatively, of course, it will all be ruled out if we get good enough data. But early data is undoubtedly going to be quite rough. So maybe it just gives us a hint of some of these features or some of the scale. Right? There could also be a gigantic normalization difference in the true reality, assuming that we could go out and measure these kinds of large-scale baryon distributions.
Thank you very much, Dylan.